Yes, thank you. So the title is probably not a very good title because I'm kind of talking about two things that are not too much related, but they're kind of on the lower end of what Linnea does and not the high-level algebra stuff. So that's why code generation is good enough of a title. Okay, so what is Linnea? The idea behind Linnea is, if we have a linear algebra problem, how do we compute it? And those are some real-world linear algebra problems that people may want to compute in practice. And what you can do, of course, is you just write some MATLAB code, and MATLAB will compute the solution, but what MATLAB does usually is not that great in terms of performance. The alternative is you take libraries like BLAS and LAPACK and write all your code yourself. It's a lot more work, you probably get better performance if you know what you're doing, but yeah, as I said, you need to know what you're doing. And we are ambitious and we are greedy, and we want the simplicity of a language like MATLAB, and we want the performance of the handwritten C code, for example, and this is what we are trying to do in Linnea. And it's not just about, well, I will show you an example quickly, yes. So, as an example, we look at this problem that's from some image processing application. And so the question is, how do we compute that? And to limit the question a bit, we just say we have those operations available, so matrix vector product, matrix matrix product, the sum of two vectors, or the sum of two matrices. And all of those operations have a cost associated to them, in this case the number of flops. And yes, we assume all operands have size n by n, or just length n vectors. And everything, yeah, everything is squared. So one thing that we can do if you look at this expression, we can either start computing the h dagger times y or the h dagger times h. And I will just start with the h dagger times h, but yeah, we could move the one of those statements around a bit because of the dependencies. And if you count the flops, this is how much work we'll be doing. So the largest term is an n cubed term because of the matrix matrix product. Now the question is, can we do better? And if you look at it like this, you maybe would not think that we can do better, but in fact we can. And one way we can do this is we start rewriting the expression, taking into account knowledge about linear algebra. So in this case, we multiply the x into the identity minus h dagger times h, and then we can remove the h dagger times h from those two terms that have in common. And now if you look at it closely, you realize you don't need a single matrix-matrix product to compute this expression. So you can do something like this. And now the largest term is an n squared term. And this is the idea behind Linnea. We don't just rewrite expressions like that, we also eliminate common sub-expressions. We look at matrix properties, we infer matrix properties, we select kernels based on properties. Yeah, that's the idea. In practice, of course, we don't just use those four operations. What we actually use is BLAS and LAPACK. So BLAS supports operation like matrix vector product, matrix matrix product, solving some linear systems, triangular linear systems, and then in LAPACK there are all the factorizations and some other stuff. Right now we're generating Julia code, but Julia has some high-level wrappers for those libraries, so it's the end result looks very similar to C. It's just slightly easier to generate Julia code. And what I'm talking about is those two things, storage formats and an algebra of banded matrices. And the reason is, well, we just submitted an extended abstract, and those two topics maybe there's not enough material to actually write a full paper on them, but I still think they're interesting and they might be interesting for you. So, and I've never talked about them before anyway. So let's start with the storage formats. If you have so in Linnea what happens is if we have our mathematical problem like this, A times B inverse times C, and B is the symmetric positive definite matrix, then Linnea will find an algorithm like this to compute it. So we apply the Cholesky factorization, solve two triangular systems, and then a matrix vector product. And this is still a purely symbolic algorithm, so we know which kernels we use, but we actually haven't figured out the details. But we still need to figure out the details and get something like this. So this is the actual Julia code that you would get. So we call the, you can see the 4 BLAS kernels that we call. And there are 2 challenges in this. One is fairly easy, it's related to overwriting, because those kernels quite frequently overwrite one of the inputs. So we have to be careful that we don't overwrite something that we don't need in the future, but that can be solved with a liveness analysis. And then we just have to copy things when we would overwrite them. The more interesting problem is related to storage formats. And to illustrate that, let's look at the LU factorization. Mathematically, what happens is, as input you have a matrix A, and as output you get 3 matrices P, L, and U. And P is a permutation matrix, so there's some 1s in there, otherwise lots of 0s. L is a lower triangular matrix with 1s on the diagonal, and U is an upper triangular matrix. And you don't see the colors very well. I'm sorry about that. But this is not actually what this kernel GTRF returns. So for the permutation matrix, you just get a 1-dimensional vector which represents this permutation, and they actually use a different format from this one. And the L and U matrix, they will be stored in the same 2-dimensional array, and all the zeros and the 1s on the diagonal will not be explicitly represented. And the nice thing is that this allows the LU, the kernel to operate in place, so we can override the input if you don't need it anymore. That's great. But depending on what we may want to do with the result, it gets a bit tricky. And a common thing you want to do with the result is you want to solve triangular systems, and there's the TRSM kernel for that. And yeah, it solves so the expression it computes is A inverse times B, and A can be lower or upper triangular, and A can have a unidiagonal. And for this kernel, we can specify which of those properties are true, and depending on what we specify, the kernel will only read this part of the array that actually contains the actual values that are explicitly presented. So we'll not touch any of the parts where it would expect a 1 or 0, because we know that this is what we would expect there. So this looks nice. It's the BLAS and LAPACK libraries. It's a system that works together, and it makes sense. But what if B is another lower triangular matrix, and it's stored in this same format where we don't actually represent the zeros? Then we kind of have a problem, because the TRSM kernel expects that B is stored as a full matrix, and it will read all entries of that matrix, but maybe not all of them are represented in memory. So we have to do something about it. So in this case, an easy solution is to just write the zeros to the part where they should be. But maybe if, again, that's the result of some factorization, then we would be overwriting something. So again, we have to be careful. And yes, so the problem is we need to know how are the operands stored that we are dealing with. Not just, well, we know what they are mathematically, but we also need to know what's the actual representation in memory. We need to know how the individual kernels read those infer operands, and we need to be able to change the storage formats whenever they are not working out. And obviously our goal is to only change storage formats when we really need it, and not when we don't need it. If you look at a language like MATLAB, if you explicitly use the LU factorization, it will give you two-dimensional arrays with all these zeros explicitly represented. It's easy, it's a nice interface, but it's not the most efficient thing you can do, so you're wasting some memory, and there will be some copies going on. Yeah. When I talk about storage formats, I don't mean row or column major. All of this can be, it's kind of an orthogonal problem to, I think, row and column major. So just to quickly go over the storage formats that you would typically encounter in libraries like BLAS and LAPACK. We have the triangular format I showed you before already. We have permutation matrices as a vector, 1D vector. We have symmetric matrices where we only store 1/2 of the elements, and again we're doing this thing where we have a 2D array and the upper or lower triangular half is only contains the elements. For banded banded matrices, one thing that you would do is you just put all the bands on top of one another in a somewhat smaller 2D array. They are packed formats both for triangular and symmetric matrices. So what we do is we take all the rows of this format is not supported as well in BLAS and LAPACK as the other format for triangular and symmetric matrices. So for LU, for example, you don't get this as output, and there's no variable, as if I'm correct, that gives you those matrices in a packed format. Then one obvious thing, which is not really part of BLAS and LAPACK because they don't do anything with diagonal matrices, is if we have a diagonal matrix, we only store the non-zero diagonal elements in the non-dimensional vector. The fairly simple solution to our problem is to define a compatibility relation. So what this tells us which formats are compatible, and the idea is here if we expect, if the kernel expects the lower triangular format I showed you for LU, but we actually have as an input matrix the full matrix with all these zeros, then we don't have a problem. If it's the other way around, we do have a problem. And so this is what the relation describes. And slightly more formally, we say that A is compatible with B if all the elements that are explicitly represented in A are also represented in B, and relative to one another, they have the same locations. So they are in the same positions. Otherwise, this doesn't work. Defining such, this forms a partial order. It's only interesting to do this because there are a handful of storage formats that are compatible. If this was not the case, then we always just had to transform the storage formats. And then the algorithm to solve the actual problem is, let's say we have a kernel and it has a bunch of input operands, and 1 and 2. For all the input operands that it takes, we want to annotate the kernel with the required storage format, so what it expects us to give it. We want to annotate all the operands that we have in our current space, that are currently live, with their current format. And of course, we need a database or some library of storage format conversions. In Linnea, it's really just a small database of code snippets that do the conversion. And then our algorithm looks like this. So for a given kernel, we go over all the input operands, and if the required storage format is not compatible with the actual storage format, we go to a library, we look up, we find a conversion from the actual storage format to some other format, such that the required format is compatible with that other format. And this is already a bit more general than it needs to be, because we could also just convert the actual storage format fi to the required ri, but since we already have this partial order, we can make use of it, and it's fine to go to something that is more general than what we need, if we maybe don't want to write storage format conversions for all possible combinations, but just save some work. We usually do those, we try to do those conversions in place whenever it's possible. Sometimes it's just not possible because it changes the number of elements from n to n squared or something. We also have to check if something gets overwritten with the LU, with the format for triangular matrices. And again, we can do a liveness analysis and we can check, does the part that gets overwritten, do we still need that? And if yes, we have to move it somewhere else. If not, we are fine. And that's it already. And yeah, this allows us to only do storage format conversions when necessary, but we are still able to basically compute arbitrary inputs with a set of BLAS and LAPACK kernels, even if the storage formats don't work out. Yes. Then let's go to our next topic, the algebra of banded matrices. The reason it's kind of related to matrix properties, and what I talked about before was also related to matrix properties, so that's the direction here. The reason I talk about this is because I think it's a very powerful formalism, but it seems like nobody knows about it, and I was kind of surprised that nobody seems to know about it, and it's not in any textbooks. So I will just present it to you, and maybe some of you find it interesting or have some things to say to it. The general idea, and this is not new, is that we represent a banded matrix as with two numbers, and those two numbers, they just tell us how many bands we have above and below the main diagonal. So here the U is what we call the upper bandwidth. We have two diagonals above the main diagonal, and L is 1. We have one diagonal below the main diagonal. And you will find this in the standard linear algebra textbook, the Golden van Loon, and the definition looks something like this. So lower bandwidth L, no, A has lower bandwidth L if I is larger than J plus L, and that implies well, you can read it yourself. But the idea is very simple. And now we can describe a bunch of common matrices with it, and including matrices that you may not wouldn't think of if you think of banded matrices. So a diagonal matrix has bandwidth 0, 0 if we just represent it as a tuple of lower and upper bandwidth. An upper triangular matrix has a lower bandwidth 0, and upper bandwidth can be whatever. In this case, we have 5 by 5 matrices. The bandwidth is limited by the size of the matrix minus 1. So here, for full triangular matrix, it's 0, 4. And then the last matrix on the right, that's an upper Hessenberg matrix, which is also something that commonly shows up in some applications. And this you will still find, so I think I actually found something like this in Wikipedia, in some article about banded matrices. But now, what if we do operations on banded matrices? So, if I add two banded matrices, okay, it's fairly easy to figure out. So, the first one is what you would call a lower bidiagonal matrix, the second one is a tridiagonal matrix, and unless those elements are perfectly cancel out each other, which I just assume they don't in this case, then obviously the part here that is 0 will become non-zero because we add something to it. And if you think about it in terms of bandwidth, what really happens is the bandwidth of the output matrix, the lower bandwidth, is just the maximum of the bandwidth of the lower bandwidth of the two input matrices, and the same for the upper bandwidth. What about multiplication? It's not as easy to figure out. The best way is probably to just take something like MATLAB and play with it. I also wrote some proof, but I'm not even sure if it's a very good proof, and that's not my area of expertise. But what you will figure out, you realize quickly, is that you just add up the lower and upper bandwidth respectively. Of course, it's limited by the size of the output matrix, which I didn't have on this slide. So, yeah, and we can do similar things. We can define this for transposition. We can do something similar for inversion, even though it's not as nice anymore. And then, basically what happens is if you have, for example, for this matrix, the upper bandwidth is 0. If you invert that matrix, the upper bandwidth stays 0. If it's larger than 0, you get whatever. But then there's a catch. I think the elements usually, they get smaller the further you go from the diagonal if you only have a small band. So, yeah, but you can still say something. And we can generalize this to non-square matrices. So, the one on the left, that's what people usually would call a trapezoidal matrix. The one on the right is, again, kind of a diagonal matrix. This is something that you get from the singular value decomposition, depending on how you use it. And all of what I said above before, the rules for addition and multiplication, they still apply to non-square matrices. We can also generalize this to negative bandwidth. So negative bandwidth really just means that we can have zeros on the diagonal, and so yeah, the idea is, okay, the upper bandwidth is -1, so if it was 0, we had elements on the diagonal, it's -1, so we don't have elements on the diagonal. If it was -2, then this band was 0 as well, and so on. Again, this number is now also limited in the other direction by the size of the matrix. And yes, there's one, you have to be careful. If the lower plus upper bandwidth plus 1 is smaller or equal to 0, then your matrix is 0. That's about it. One not so nice thing that you can have is eventually you get some cases of over-approximation, both with a negative bandwidth and with non-square matrices. So in this case, we multiply those two matrices, and remember we sum up the upper and lower bandwidth respectively. So 3 minus 1 is 2, minus 2 plus 4 is 2, so we would expect what you would call a pentadiagonal matrix. In practice, those elements over here, they're all 0. It's not much of a surprise if you look at the structure of those matrices and where they have the zeros. But still, this doesn't break the formalism, because the formalism also only talks about what happens outside of the bands and not what happens inside of the bands. So that's perfectly fine. But you still may want to do something about it. Finally, and I really like this part, this algebra is closed under partitioning. So with the extension to negative bandwidth, and also to non-square matrices. So you take any of those banded matrices, you partition it in how many parts you want, in any way you want, and all the parts can still be described as banded matrices. And computing the bandwidth of the parts is really just a geometric problem, because all those lines here have a slope of 1, so you just need to compute where do they intersect, and then you know the bandwidth of all the parts. In Linnea, we use this idea to infer matrix properties. So we ask the user to provide us with a description of the properties of the input operands, and we want to figure out how do they propagate as we do some computations. And with this, we don't need to write a large table of all the properties and all the combinations and check what we have. For a lot of them, we can just do a little bit of math and know what we have. The only other place where I ever saw this mentioned is in some GitHub issue for the Julia language, and they were talking about maybe incorporating that into their type system, which I also think is a nice idea. Yeah, how easy or difficult it is, I don't know. They didn't, it's a couple of years old, and I don't know, I don't think anything has happened since then in that direction. Finally, maybe this would help us to have better support for banded matrices in libraries, because my impression was that, well, if you start looking for a product of two banded matrices, I once had a student do that and he didn't find anything. So, yeah, there's still some. BLAS only does banded matrix times vector and some other operations with one banded matrix. To end with some pretty plots, I will show you some results for Linnea. And so this includes, those results are not limited to any of what I showed you before, so this is just everything that Linnea does. So all the rewritings, storage formulas, inferring properties, that's all in there. We look at a couple of different implementations. So if this is our mathematical problem, then the naive implementation that, well, we compared against MATLAB, Julia, and Armadillo. The naive implementation is the one-to-one translation of the mathematical problem. People will tell you that's not what you should do because there's an explicit inversion, so instead, please solve it in a system. So we also compared with the recommended solution. And finally, our generated solutions by Linnea look something like this. We have 125 example problems, 100 random ones, 25 example problems collected, real-world example problems collected from papers. Some are all of them, the ones on the first slide are in there. This is the speed up of Linnea as a factor over all the other competitors. they're sorted by the intensity of the solution found by Linnea, and you see we easily get speedups of 2, 5, and even higher. This is the single-threaded case. Libraries, so all those, Julia, MATLAB, Armadillo, they all use BLAS and LAPACK underneath, and we all use we link them all against the same implementation in Intel MKL. And what we also, those libraries are parallelized already, so what we just did in another experiment, we just enabled parallelism in BLAS and LAPACK, and what you get is this. So for 24 threads, we get even larger speedups, which is probably because we have less overhead compared to the competition. You see there's some cases where the competition performs better, though those are mostly low-intensity cases. It's also, so far, Linnea doesn't really do anything to find good solutions for the parallel case. So it's just, there's still work that can be done. But still, we easily get a 10x speed up and even more over all the competitors. And that's about it. Thank you very much.
So you have a number of conversion functions that you were looking for in the library for those things. Are there costs associated with doing the copying, or I mean, in some cases there must be different ways of first you could convert something, then you apply some operation, and then you're in a situation where you don't have any problem with aliasing, and another situation where you could do it. First do the operation and then convert?
Unfortunately, we don't have a lot of, when we use something like BLAS and LAPACK, we don't have a lot of choice in terms of selecting kernels by the formats that they use, because BLAS doesn't really offer all the kernels for all the formats. So it's usually, we select the kernel based on the number of flops, and we select the best one in terms of flops, and then we figure out what do we have to do for the storage formats to make this work. So yes, so far this is kind of a greedy approach, and there are some rare cases that I've seen already where the storage format conversion adds a little bit of overhead that maybe some of the competitors don't have.